SDU time is now 1:15, and we have, I'm happy to see we have more than 25 participants, so it's really my pleasure to welcome you all to this DIAS lecture. My name is Asger Mortensen, and it's really my pleasure on behalf of DIAS to introduce you all to Joel Cox. Joel is a well-known face. He has been for now quite a while an assistant professor at DIAS and also affiliated with the Center for Nano-optics. Recently, Joel was granted one of those prestigious grants from the Sapir Aude Young Researcher Program, and I guess we will hear more about this from Joel in a while. Before coming to SDU, Joel was at a research facility in Barcelona called ICFO, which is one of the top facilities in Europe, focusing their interest into optics and photonics, light-matter interactions. And when coming to SDU, Joel also brought a range of interesting research topics centered around explorations of light-matter interactions in 2D materials. And this is also the basis for the project that Joel has now been granted from the Sapir Aude program, and which you will hear more about now. For the record, I should just mention that the lecture is being recorded, including the conversations we will have after the lecture and the questions and the comments. And with this, it's my pleasure to hand over the floor to you, Joel. So please.
Okay. Well, thank you very much, Asger, for that kind introduction, and thank you all for tuning in. Right, I'm a theoretical researcher in the Center for Nano-optics, and I'm trying to relate my theoretical research really closely with experiments in 2D materials or noble metals, and always with this with technological applications in mind. So today I'll be discussing a bit about the research I've been doing in the areas of nanophotonics with 2D materials, and also in nonlinear optics. Right, but first, I think I'll start just by trying to convince you that research in optics and photonics is important. And I don't think this will be very hard to do. Particularly given the present circumstances we're in right now regarding the COVID-19 pandemic, and just the fact that I'm able to present to you from the comfort of my home to you and yours. And this is all, of course, thanks to the internet, right? Which, of course, is due in large part to the vast network of cables, fiber optical cables running underneath our oceans. So the joke is that the cloud is not really up in the cloud, but actually underwater, right? And we use fiber optics because we can then transmit information at the speed of light, right? And actually with minimal power consumption, right? So this is really the backbone of the internet, and it's super important now in our everyday lives. But then you might notice, of course, at the end of this journey, the information we process, it ends up on your computer, right? And if your computer is anything like mine, it's running on electricity, right? So electrons are doing the computations and transmitting information and so on. So at some point in that journey, we're transmitting optical signals to electrical ones, right? So if we look at the situation, generally we have, of course, the internet and the magic of fiber optics, right? And then we have these vast data centers, such as the one that's recently been built in Foon for Facebook, right? In Odense. And then this is somehow ending up on our computers, right? So we're just able to talk to each other all over the world. And at every point in this journey, well, many points in this journey, we're somehow shunting information from, again, optical to electrical signals. And each time we do that, we're kind of losing in terms of efficiency and also speed. And this has motivated already a lot of research in finding ways to sort of circumvent this limitation, because these data centers are already becoming an enormous drain on our electrical grid, and in terms of sustainability, it's just not great. So the idea is that if we can replace electronic components with photonic ones, then we'll win in several ways. And this is the overarching challenge that we're facing. So then that sounds quite good, right? Then it's simple. We just have to swap electrical components with photonic ones. But then I'll try to explain why this hasn't happened already. So if you remember back in high school physics, you probably learned that light is an electromagnetic wave, right? And it carries both energy and momentum. And we characterize these electromagnetic waves in terms of their wavelength, right? We can talk about the wavelength of light, and that determines a lot of its properties. And if we think about visible light that we deal with every day, just by seeing, then we're talking about wavelengths in the range of a few hundred nanometers, between 400 to 700 nanometers, right? Now, actually, because light is a wave, though, this places a fundamental constraint on how small we can resolve things spatially. So how strongly we can focus the light, it depends on the wavelength that you're using. And this is a well-known limit. This is Abbe's diffraction limit. And it basically tells us that we can't focus light on length scales that are much smaller than its wavelength with conventional optical systems, right? So here you can sort of see the length scales that we're talking about, going down from an ant to the human hair, down to cells, and then just missing the viruses, maybe just missing our COVID virus here, because we're around 200 nanometers roughly in terms of how strongly we can focus the light, again, using conventional optics. Now, this makes it really hard to compete with electronics because, as again, many of you I'm sure know, we're able already to cram literally billions of transistors onto single integrated circuits in computer processors, for example, right? So here's a replica of one of the original transistors back in the 1950s. This was when the whole digital information age started, and now we have tens of billions of these in our computer processing chips. And this, of course, the rate of how many we've been able to cram into these chips has been growing. Every 2 years, it's supposed to double according to Moore's law. And then you might notice nowadays, this is actually beginning to slow down. And there's a number of reasons for this. And one of the most obvious is simply that we've gone so small that it's hard to actually manufacture these things. And we're talking about 10 nanometers, roughly, is the size of an individual transistor. Now, if you may remember, the diffraction limit is preventing us from really getting light into the same length scale. So we can't even think about having the same kind of photonic, let's say, density. But there's an even more problematic issue. It's very fundamental. And that's simply that light doesn't work the same way as electronics, right? Electricity, we're able to sort of turn it on and off using electricity. So electrical signals can manipulate themselves. But this isn't really so easy to do with light, right? So if we think about light matter interactions in our everyday lives, we're used to simple phenomena such as light being transmitted through a material, like when you look out the window and you can see through it. Light could also be absorbed by materials, right? This is what we're trying to do with solar panels, for example. Or simply light can be reflected by materials, like if you look in a mirror. And then often all of these three things are happening at once. And then there's also refraction. I'm just skipping over that. But these are sort of, we can say, linear optical phenomena in a way, in the sense that the light we're talking about is sort of weak. It's not very intense like the light you get out of a laser. And so the amount of light, for example, that's absorbed is proportional to how much light you send in, right? It's linearly proportional. And that's why we call this sort of a linear optical phenomena, at least in our everyday lives. But if we want to somehow manipulate light with itself, we have to turn now to nonlinear optical phenomena. And then we have light matter interactions that are inherently dependent on the intensity of the light that's involved, right? So one very well-known example, which was actually sort of the first example to be experimentally demonstrated just after the laser was invented, it's known as harmonic generation. And it's a process where intense laser light interacts with material. And through that interaction with the material, it's actually able to interact with itself. And that allows the light, essentially, you can think of it like it's combining with itself to create electromagnetic waves with higher frequency, right? Doubling or tripling the frequency. And we call this second and third harmonic generation, respectively. And you can describe it through this expression. If we talk about the polarization of a material, which characterizes its response to light, we have this linear term that I was discussing earlier. You can see it's linearly proportional to the electric field. And then you have these nonlinear terms that depend on higher powers of the field, right? This chi2 and the chi3 assess roughly the strength of this nonlinearity. So some materials have a better chi2 or a better chi3 than others. And actually, in most materials, these nonlinear susceptibilities, as they're called, are incredibly low. So this is why we haven't been able to see this for, well, it's been a long time now since this was first discovered, but it's not so familiar because we're not usually dealing with intense laser fields or intense light that lets us access this regime. So you can also think of this in a more sort of quantum mechanical way of 3 photons somehow combining to create a photon, for example, at 3 times the energy. Now, another sort of fundamental nonlinear optical phenomenon besides this frequency conversion, you also have a nonlinear absorption. And what that is a phenomenon where the intensity of the light that you illuminate a material with can sort of quench its ability to absorb light, right? So you have an absorption coefficient that tells you how the intensity of the light is being absorbed by the material, how it's exponentially decaying. And then in the nonlinear regime, we say that this actually depends on the intensity of light that you use. So if we come in with strong enough light, we can make a material transparent, right? This is the basic idea. And then you can already start to imagine ways you can use this for developing, say, optical switches. So what I've discussed is sort of the traditional nonlinear optics that has been around since, again, the 1960s. And it relies on really intense laser fields. And often we're talking about special crystals that have these larger nonlinear susceptibilities. And also we want to have more volume because if there's more material and light interacting with the material, we can accumulate a larger nonlinear response, right? So then we have ways of converting laser light to different colors, literally, and also ways of encoding information on one field using another, right? So now we're talking about optical switches and things like that. But again, we're limited by the constraints of the power demand because we need intense lasers. And also the size of the crystals is important because their nonlinear interaction with light is weak. Where we want to go with this, the ultimate limit, let's say in terms of efficiency, also in terms of size in a way, we can talk about quantum nonlinear optical phenomenon, where you have literally just a single photon and the smallest unit of light, right? And a single atom, which is the smallest unit of matter. And we somehow make these nonlinear phenomena happen. This is tough to do because the photon may or may not see the atom, right, when it passes by. But one way you can help increase the likelihood that this will happen, that these interactions can take place, is if you put the atom between, say, 2 mirrors. So in this, we form what we call an optical cavity, and the photon is kind of bouncing back and forth between those mirrors, and eventually it will find the atom. So then you can imagine the quantum analogs of these nonlinear processes that I've been mentioning, like individual photons coming in, mixing and creating a higher energy photon, or a single photon coming in and preventing the absorption of another, right? This is a photon blockade. Okay. So what I'm describing is not really new to people working in quantum optics. It's kind of actually, I would say, routine for them. There is a lot of research going on, even at SDU, where we're talking literally about individual photons and individual atoms interacting. The problem, though, generally, is that you kind of need to do this in the lab on big optical tables with lots of mirrors, lenses, all this fancy equipment. And then when you're talking about individual atoms, you have to also find ways of trapping them and putting them where you want them to be. So you can have optical traps that can place them in the right positions and they can interact and so on. So this is all important fundamental research, and it's very useful for quantum information. But the overarching strategy we're looking at in nanophotonics or nano-optics is to take all these ideas and somehow put them down into the nanoscale, right? And to think about how we might be able to develop integrated photonic devices, even talking about quantum optical information processing in devices like what we have now in our smartphones and our computers with billions of switches and so on. So this is the general idea. Now, how can we go about doing this? And this is where in the Center for Nano-Optics, we're doing a lot of research on plasmonics, right? So I'll try to explain what that is as a fundamental concept. This is what we always say, that plasmons are collective oscillations of the conduction electrons in metals. Of course, that's true. What that means is that if you come with an electromagnetic field, like so light, that is you say the electric field is varying in time, right? When the electric field interacts with a gold particle, just gold, for example, or silver, the electrons in the metal are free to move, right? So they'll be displaced by this electric field. And on the other side, when they're displaced, you have actually the positive ion cores of the atoms that make the particle. They're trying to pull the electrons back, right? So the analogy to this is a simple harmonic oscillator. You can think of a mass on a spring, and it has a natural resonance frequency at which you can sort of deliver energy to the oscillator more efficiently, right? So these are the Plasmon resonances, and effectively what they do is they concentrate the light in the vicinity of the particle. Actually, what they do, they can also sort of not artificially, but effectively enhance the absorption cross-section of the particle. So all the light coming in is sort of funneled into this plasmonic particle, and it appears somewhat larger than it actually is. So the light can more easily find it, and it can be focused into small regions in space. And then you also have the analog of this in a flat metal surface, these Plasmon Polaritons. So we have oscillations of electrons here that can be hybridized with light. And effectively what this is doing, it's like this optical resonator that I talked about earlier with the atom between two mirrors. This is like the two mirrors. It's kind of concentrating the light for you into the surface of your metal or your metal particle. So we can actually control the Plasmon resonances by tailoring the composition or the geometry of the materials that we're working with. And typically we're talking about noble metals like gold and silver. By shortening the size of the particle, for example, essentially the oscillation is like a standing wave. So if you shorten it, you shorten the wavelength, which means it boosts the energy. So now you're talking about, for example, UV or blue light. A longer particle should have a longer wavelength, right? So it has a lower energy resonance in the red, it could be. And the absorption is represented here, for example. This is just a characteristic example of a metal particle. By changing the size of the particle, you can tune the wavelength at which it absorbs light most strongly, because you're tuning the Plasmon resonance. And then again, the light is focusing incredibly intensely in the vicinity of the particle, right? So the electromagnetic field is strongly enhanced in small regions in space. So there's a lot of appealing applications for plasmonics, and I'll just highlight sort of a general overview of what are some of the most promising applications. One that's widely discussed, it's even finding applications outside of the lab, is optical sensing. So the Plasmon resonances in these particles or on metal surfaces are sensitive to the dielectric environment around them. And if you treat the particles or the surface so that they have receptors that will catch particular biological entities that you might want to detect. Some markers, for example, for cancer. You can imagine that they'll bind to these receptors and they'll change the effective dielectric response, changing the plasmon resonance. And you can detect that change and then determine whether or not you have this analyte present or not. There's also a lot of interest in using plasmons to focus light into atoms or sort of well, natural atoms or also artificial ones. And this has a lot of applications in quantum optics. In particular, we can use the plasmonic near field to control this rate of spontaneous emission from atoms. And this is really useful if we're talking about trying to miniaturize quantum optical systems. Of course, if you're focusing light, you can always think of solar energy and somehow boosting the efficiency of our solar cells using plasmonics. And then again, when the light is concentrated, we can, of course, talk about nonlinear optics, and that's what I'll get into later, but this is actively explored in plasmonics. And then there's also ways you can use the near field enhancement to control chemical reactions, actually, on very small length scales, either through directly through optical changes or triggered by the heat that's created when you excite plasmons resonantly, right? So you're delivering a lot of energy to the electrons and they're oscillating. It actually causes them to heat up, and that heat can be diffusing out into the environment. And you can sort of have a nanoscale source of heat. So I'll focus mainly on a few of these applications I mentioned, in particular, as a general concept, the idea of atom-plasmon interactions, where the light is sort of being focused and then it interacts with an atomic system that you have nearby, right? That you want, maybe you can't see it easily because it's so small, but then the plasmonic enhancement of the near field will effectively allow you to couple that light more efficiently. And there's been a number of experimental studies on this. Just by creating special nanogaps, you can have molecules that will see a much stronger electric field than they would otherwise. And then nonlinear plasmonics, as I already mentioned briefly, we can sort of focus the light into metal nanostructures and force it to interact with itself, to force these nonlinear interactions, and they can occur more efficiently because of the plasmonic enhancements that we engineer in a certain way. Right, so here's a few examples. For example, in second harmonic generation is widely studied in this context. Now, there, of course, are a few disadvantages to plasmons, and I'll mention them here. In noble metals in particular, which is being widely used for plasmonics, you have intrinsic losses, right? When the electrons are moving around in the metal, they're going to scatter with each other, with impurities, with the ions of the lattice in the crystal. And these losses can really diminish the performance of your device. They generate, you want the plasmon to oscillate strongly with the light, and you don't want it to lose its energy or decohere very quickly. But unfortunately, this is what's happening. And so here's kind of the grief cycle that we've been facing in this field, right? So we've got really excited at the beginning with the smaller and faster devices. And then we realize the losses are kind of ruining the party. You go through all these phases, anger, why aren't there better materials, this sort of thing. Actually, there's a lot of ways you can even harness the loss. I mentioned this thermal engineering. That's actually one way to do that. And then there's plenty of applications in that area. But then we can actually start to look at different materials, and I'll talk about that in the next slide. But the other disadvantage of noble metal plasmons is that you can't really, I mentioned that you can tune their resonances by changing their composition or geometry, which is fine when you're fabricating them. But then if you want to make a device that can be tuned on and off, actively switched, this is a problem because you can't easily change the size of your metal particle, right? So this is another limitation that we face in this field. Now, in noble metal plasmonics, there's a recent trend now that actually is being explored at SDU, in the Center for Nano-Optics, to go to new types of noble metals. So they do have these losses, but you can make them better. essentially. If you can make them actually completely crystalline, you already win just by having a more ordered system. It can be atomically flat, so you start to sort of iron out the wrinkles, and you can have, ultimately you can have a higher quality plasmonic resonator. So this is something we actually have access to at STU, and there's been a lot of experimental research in this area. And actually in my former group at ICFO, they've also been looking at crystalline noble metals and making them incredibly thin, just down to a few atomic planes of thickness, right? We're talking about 14 monolayers of silver in this case, with a very well-defined crystallographic orientation. So these are kind of state-of-the-art noble metal materials for plasmonics that are starting to attract interest just in the last few years, and they're becoming more widely accessible. So this has kind of triggered us to look at this from the theory side now, and this is a collaboration of us at STU with my former group at ICFO. And we want to look at how we can characterize the optical response of these high quality crystalline noble metals. And one way to do that is to perform semi-atomistic simulations of these crystalline materials to find their optical response, and from that extract surface response parameters, surface response functions that contain within them a lot of the information that you get out of a really heavy numerical simulation that takes into account quantum mechanical effects in the electronic band structure of the metal due to the crystallographic orientation, also including surface states that appear for certain facets, for certain crystal facets. They can all be contained in these simple Feibleman-D parameters, and we tabulate those sort of once and for all, and they can be implemented in electromagnetic simulations of various metal morphologies, also in nanostructured thin films or small particles. And this kind of helps both in theory and experiment to describe these new types of materials and capture the quantum mechanical effects that could affect their optical response. Also in parallel with my former group at ICFO, we have a collaboration to explore these crystalline noble metal thin films in the context of nonlinear plasmonics. So if they're higher quality plasmonic materials, also if they're incredibly thin, they have more surface to volume ratio, they should offer a more intense nonlinear optical response. So we're using atomistic theory that we've developed to describe the nonlinear optical phenomena in these systems. And you can think of things again like harmonic generation, but happening on the nanoscale, actually excited by a localized source, like a metal tip that can launch plasmons, and they can be upconverted through nonlinear optical processes. And again, what we find is that you can also tune the nonlinear response by changing the thickness of the material in terms of the number of atomic planes you have. And in going to very, very thin materials, you win in a way because you take advantage of the quantum finite size effects that you get in the electronic structure. So you can see that the electronic density of states here is very different for a small film with only 5 monolayers compared to a thick film with 100 monolayers. So this is meant to motivate further explorations in that area. Right, but I mentioned that we have 2 limitations in plasmonics that we're currently facing. The first is the area of losses being very high, and the second is active tunability. And then in the last 10 years or so, there's been an explosion of research in graphene as a plasmonic material, right? So graphene is a atomically thin layer of carbon atoms, right? So you can see a small piece of it here. And the really interesting thing about graphene, well, one of the interesting things about graphene is its electronic dispersion relation. So it has these linearized electronic bands that is very different from what you find in conventional materials, right? And from a technological standpoint, what's really fascinating about graphene is that if you just have graphene isolated in vacuum, it has this simple band structure where electrons are sitting in this low energy cone. So it's like a zero gap semiconductor. But if you can apply an electric field to the graphene, you can effectively increase the charge density in the graphene layer, so adding some electrons. We call this doping the graphene. Then you can increase its Fermi energy, so the highest occupied state in the electronic structure, and it essentially becomes a metal. So it has electrons that can sort of move around here in this dispersion relation, and you can describe it by this simple optical conductivity, right, that characterizes the optical response. And moreover, it's a high quality metal in the sense that it has relatively lower loss than gold and silver, let's say. So the two main points are sort of addressed here in the fact that you can electrically tune the charge density, and therefore you can electrically tune the Plasmon resonances, and also that the Plasmon resonances seem to have a higher quality. So there's, as I said, there's been an explosion of research in this area, and here I've highlighted a number of experiments where the graphene plasmons have been sort of imaged in real space using scanning near-field optical microscopy. So this technique, in this technique, we have a metal tip that effectively excites the plasmons, right? And they sort of propagate away and they come back, and then you can see them from the light that's outcoupled. And then you sort of move the tip around as you're doing this, and you can sort of create a map of these charge density oscillations in your 2D material. So it's a really impressive tool, but you need this tip because the plasmons in graphene are so strongly confined that you need to deliver a lot of extra momentum to launch them in the first place. And that's what the tip is doing, actually. It's giving you a point source of light that has all the spatial spectral components there, and it can couple to the plasmons. Now, another strategy, though, rather than using this AFM tip, if you actually pattern the graphene into small resonators, then you can have localized plasmons that don't propagate, but they're sort of standing waves that form in these particles of graphene, you could say, just like in the gold metal particle I mentioned earlier. And there you can tune the Plasmon resonances by changing the geometry of the graphene, or also by changing the charge density in the layer, right? So by changing the Fermi energy, you can actively tune the Plasmon resonances to different wavelengths and change the absorption. So this has been demonstrated in a number of experiments. There have been some reports of actually achieving perfect light absorption in graphene nanoresonators arranged in a periodic way. This was just a theoretical prediction up until a few years ago, and then it was experimentally demonstrated using ribbons of graphene combined with ribbons of gold, right? And you can see they can achieve 100% absorption at a specific frequency that depends also on the Fermi energy. So this is already quite amazing because it's just a single atom layer thick of carbon, and it's absorbing 100% of the light. We can also use this in terms of biological sensing. So we have these graphene plasmon resonances that they themselves can be influenced by the optical properties of an analyte molecule. So it might have an optical resonance of its own. And this interaction of the two resonances can effectively tell you something about the particle that you might want to detect, right? At these particular frequencies, for example, you might have a specific signature of that molecule, and then you're able to detect it by sweeping the graphene plasmon resonance. Now, another area we've actually recently been working on at SDU, this is actually building on research from a former member who recently went to ICFO, Andre Gonçalves. So he was proposing to make plasmonic waveguides that can transmit electromagnetic energy in one direction. And one simple way to do that, rather than patterning the graphene, might be just folding it. So you kind of you engineer a waveguide using, let's say, the flexibility of the material, right? So we've actually been exploring this in more detail and looking at what happens if you just do it a bit more gently, rather than having a sharp corner. Although the sharp corner will definitely help you confine the light more strongly. Here you have literally some flexibility in how the graphene is bent, and that could be one way to form a plasmonic waveguide that transmits light in the 2D material. One area I've been looking at quite a lot, coming back to graphene nanostructures, is how to tune the plasmon resonances so that they can be used in the visible regime. So you might have noticed in some of the earlier slides that the energies of these plasmons are characteristically low in graphene. They're kind of in the infrared regime. And In noble metal particles, you have them in the visible regime. And this can be a technological disadvantage depending on your application. But one simple way to boost the plasma resonances to higher energies is to make your graphene nano islands smaller and smaller. And just the confinement alone can push up that energy. And then you can also increase the Fermi energy in graphene to further enhance the energy of the plasmon. So this is a good idea in general, but then when you get to really small sizes, you start to run into issues because you have to deal with quantum mechanical effects that play a really important role in the optical response of these small islands, right? So for this 10 nanometer triangle, just as an example, you can already see a few differences between a model where you predict it as just a uniform homogeneous material that's shaped like a triangle, and you solve electromagnetic equations that describe it. But you can see a difference if you do the simulation atomistically, using even just a simple type binding model, but you include a self-consistent electron-electron interaction, right? And typically the plasmon energy is scaling with the Fermi energy, right? And inversely with the size of your island. So if you keep making it smaller, you can start to push the resonance to higher and higher energies. And here, by the way, I'm plotting the absorption cross-section of the island. So you see a strong feature where the plasmon resonance is, right? Eventually going down to molecules of graphene, just containing tens of atoms. Of course, then you might not even call it graphene, but rather polycyclic aromatic hydrocarbon that you've managed to charge somehow. But this has already motivated a whole branch of research in what we call molecular plasmonics, right? And now I should also mention that besides being a really appealing candidate material for plasmonics, graphene is also intrinsically nonlinear. Its response to light is intrinsically nonlinear. So it is actually already quite good for nonlinear optical applications. And a lot of this is already coming from its electronic band structure, which is, again, it has this linear property. So for example, if you have a nonlinear process where different frequencies of light are involved, either that they're excited with different frequencies of light, or you're generating a new frequency of light, you can always find, because of this linear structure, you always find a transition going across these two bands that you can couple the light to. And that can already give you some kind of enhancement in the optical nonlinearity, right? So for some process like wave mixing, where we have 3 different frequencies involved, this can already give you a boost. But another appealing property, let's say, is actually if you just look at the electron motion within these bands. So if an electron is being driven by an electromagnetic field that's oscillating in time, it goes back and forth across this band. And as it does that, effectively what happens is its velocity doesn't change magnitude, but it changes its direction instantaneously. So the currents will look like this square wave, right? Going from one side to the other, going from one direction to the other, dramatically changing. And this is already giving rise to intense harmonic generation of light. And that's in stark contrast to conventional materials described by a parabolic dispersion relation, where you sort of just recover a response at the fundamental frequency. So they're very linear. So what I've been doing a lot in the last few years, and a lot of the research I've been doing actually is reported in this review and accounts of chemical research. So if you're interested, I encourage you to please check it out. But the basic idea is to combine the appealing nonlinear optical properties of graphene with its appealing plasmonic properties. And then we have this sort of a subfield, this marriage of both in nonlinear graphene plasmonics. In this area, I've been mainly performing atomistic simulations of graphene islands, looking at their nonlinear optical properties, also in graphene nanoribbons and other morphologies, and trying to sort of understand it and also to show that it actually is superior in many ways to conventional plasmonic materials like gold and silver. Right, so here we find already that second and third harmonic generation in graphene compared to these conventional particles, just predicted in theory, of course, but it's orders of magnitude higher, and this definitely warrants further experimental investigation in these systems. Also for graphene nanoribbons, we see dramatic optical nonlinearities. We have these nonlinear susceptibilities that are very high, The numbers are probably meaningless to most of you, but these are actually very good numbers. So it means that the graphene should be able to enhance the nonlinear optical response dramatically, particularly when you excite the plasmons, right? And then typically, we've also been interested in the quantum finite size effects that you might run into when you get to very small sizes for your structures, right? But typically when you're above 10 nanometers or so 20, 30 nanometers, you can already go to a simpler model that treats the graphene as a homogeneous 2D structure. There's been a few proposals to use the nonlinear optical response for, say, quantum optical applications. So this is one where I was proposing to actually upconvert light at the Plasmon resonance to, say, the third harmonic. And then you can interact the graphene plasmon through this nonlinear process with a quantum emitter that has a resonance frequency at a much higher energy. And then you still maintain the ability to actively tune the graphene, and therefore you can tune the optical properties of your quantum emitter. So in this proposal here, I'm showing, for example, the Rabi frequencies that you would see if you were illuminating this hybrid system with a monochromatic laser field. This would be the sort of the characteristic frequency of the excitation in the emitter. And by changing the Fermi energy in graphene, you can change how that happens, the strength of the interaction, also the frequency. So, of course, if you move the emitter closer or further away from the graphene island, you can tune that response. But what's more interesting is if you actually just leave the emitter and the island alone, well, except you electrically gate the island, and then you can electrically tune the plasma resonance and change the interaction of the island with the emitter. Right, so this gives you essentially an electrical knob you can use to tune the properties of the quantum emitter and therefore the light that it might be emitting or absorbing. I've also been looking at how you can go for extreme nonlinear optical phenomena when you illuminate with really intense electromagnetic fields. You resonantly excite the plasmon and you can generate high order harmonics, right, of the plasmon that you've resonantly excited. And this, of course, occurs more efficiently when you, again, when you resonantly excite the plasmon. You can see harmonics, just not only second and third order harmonics. Here we're going for second, third, fourth, fifth, up to 13th or something. So this is also a way you can generate intense ultra short light pulses. So just to save on time, I think I'm running a little long. I'll just mention briefly that this process is an extreme nonlinear optical process. So it means that you really strongly excite the graphene. It means you deliver a lot of energy to the graphene plasmon. It gets absorbed, and you can dramatically increase the temperature in the graphene island, just the temperature of the electrons, which in turn is sort of like optically doping your graphene nano island. So you can already, rather than electrically gating the system, you can optically dope the system, because again, it's very susceptible to changes in its electronic structure. So this was leading to a proposal of using this phenomenon to deliver sort of dramatic changes in the optical response just through the absorption of an individual photon, or rather an individual plasmon. If a single plasmon is absorbed in a small enough graphene island, it can actually thermalize very quickly, changing the optical response. So you can see a noticeable change in this absorption peak just by absorbing the energy of the plasmon when the system was at room temperature, let's say. So this can already be, you can already imagine how this might be used if you combine it with a quantum emitter. Sorry, I should also mention that this was studied both using classical models and also atomistic descriptions for very small islands, but qualitatively the physics is the same. Actually, for smaller islands, you're more sensitive to quantum finite size effects. But the story is, at the end of the day, if you can couple this quantum emitter to a graphene island, and it is excited by an optical field and decays, spontaneously emits light, exciting a plasmon, that plasmon will then be absorbed by the graphene in the order of tens of femtoseconds, and it will trigger a dramatic change in the optical response. So already you have sort of a single photon blockade effectively, because the next absorption event won't occur in the same way since you've moved the optical resonance. More things to do with individual plasmons. We had a collaboration with researchers in Vienna who are specialists in quantum optics, and they wanted to develop a system where you have essentially a system that's so nonlinear, you have two-photon absorption. So the absorption of two photons simultaneously is stronger than the absorption of a single photon, right? It turns out graphene can do this in nanoribbons. And the idea here is to combine the two ribbons to form a kind of what's called a swap gate, a square root of swap gate. Effectively, if you have two plasmons coming into the input nodes of this device, you want to have a situation where there's a superposition of them being swapped and not swapped. So going across the gate or not. The issue is that in this configuration, you normally get the plasmons bunching. So they'll always exit on the same waveguide. And we want that not to happen. So if the two plasmon absorption is stronger than the single plasmon absorption, this won't happen just by construction. And effectively, you can use that for certain quantum information protocols. More things. How much time do I have? Asker, sorry. Just.
So we should leave some time for discussion also. But
okay, I'll finish up. I'm almost there. So another really recent idea using the nonlinear response of plasmons and graphene. Rather than individual photons, what about individual electrons? Right. So electron energy loss microscopy and also cathodoluminescence are both widely studied in nanophotonics. And the idea is simply that you can, rather than using light, you can send an individual electron, and the electric field of that electron will excite a plasmon in your nanostructure. And then that plasmon will radiate light into the far field, for example. It turns out that under the right conditions, you can actually trigger observable changes because of this electron moving very, very slowly. So if it's moving very, very slowly past the island, there's more self-interaction and more optical nonlinearity, and you can effectively quench cathodoluminescence or shift to different frequencies in these graphene islands. And finally, just a few months ago, with these researchers in Vienna I mentioned who are doing experimental research, they were able to show that combining graphene with a metal nanoribbon can really dramatically enhance its nonlinear optical properties. In particular, for third harmonic generation, they were able to observe a substantial effect. And they were also able to show how you can tune the nonlinearity through electrostatic gating of the graphene. So again, you can actively tune the nonlinear response. So just now to say a few things about where this is all going. The conclusion is kind of simple, that graphene plasmons show a lot of promise for nonlinear optics and in general as a 2D material platform. And now where this is heading is to look beyond graphene. Of course, graphene has a lot of advantages, but it also has disadvantages. Like I mentioned, that its plasmons are typically at lower energies, and they still suffer from losses like in noble metals. Although it may be a bit better, they still have their own problems. So ever since graphene was first mechanically exfoliated, now there's been a huge number of 2D materials that are being isolated, and they all have their own sort of distinct optical and electronic properties, and they can also support other kinds of polaritons. So the Plasmon Polariton is just one kind of polariton in the family of possible hybrid light matter excitations. You also have exciton polaritons or phonon polaritons, where the light hybridizes with vibrations in the material. And these can also do the same job of trapping light at the nanoscale. And again, acting like this optical cavity that we want to use for single photon nonlinear optics. So the idea is to simply replace the optical cavity with these 2D materials, which are by construction extremely small, right? And they show a lot of appealing properties like electrical tunability, not only in graphene, but also for other 2D materials, as we're finding out. And what, from the theory side, what makes sense is to start simulating the optical properties of these systems and trying to figure out what are the best possible configurations for achieving in extremely efficient nonlinear optical interactions. Ultimately, we want to go for this level of single photon optical nonlinearity, which would be the most efficient possibility. And there's tons of candidate systems. We can even think about how to combine the 2D materials in many different ways, like this analogy with Lego bricks. Also, we don't have to forget entirely about metals, but we can think now about atomically thin metals. As I showed you earlier, that's becoming closer to reality. We also have other versions of graphene, like carbon nanotubes, also twisted bilayer graphene, which was recently found to be superconducting under the right conditions. Beyond that, we can think about not just restricting ourselves to 2D materials, but looking at slightly 2D materials that are made of maybe a few atomic monolayers, right? So metals with a few atomic monolayer thickness. And then again, also interfacing, say, graphene with these metals, we can have extremely concentrated polaritons, these so-called acoustic plasmons that give dramatic enhancements in the light-matter interaction. So that brings me to the end of my talk, and I hope it was interesting and that you learned a few things about what we're doing in the Center for Nano-Optics. The takeaway message is relatively short and simple, that there are a lot of appealing prospects for nonlinear optics using these 2D polaritons, including electrical control over the nonlinearity, and ultimately we want to go for this single photon level optical nonlinearity. I'll just also say you can find details in these review papers that I've recently published. This accounts of chemical research is about the graphene plasmons mainly, and the nonlinear response, whereas a more general review is here in advanced optical materials. So please have a look. And I thank you all for your attention.
Thank you, Joe. Maybe I can first start by just encouraging you to briefly comment on also the temperature effects and the possible existence of these effects at, let's say, room temperature, that is making it much more, I guess, relevant also to practical use.
Yeah, like the nonlinearity in general, you mean?
I mean, the possibility for all this to work and manifest at ambient conditions rather than in low temperature labs.
Yeah, I think there are definitely a lot of possibilities there. And most of the experiments on graphene are already being conducted at room temperature. To go to truly single photon level optical nonlinearity, that would definitely be a bit more challenging. But there could be ways of, like I was showing earlier, there could be ways of even exploiting the thermal optical response in materials like graphene that are intrinsically susceptible to temperature effects. There you might be talking about losing coherence, so it might not work for all applications, but just as a concept, it's already sort of extremely efficient, let's say. And then, of course, we've already seen from Sergei Morozov, right, that you can already see the electrical tunability in atomically thin semiconductors just by at room temperature, just through electrical doping.
Good. Let me invite everybody to ask questions now and offer your comments, etc. So please indicate if you have any questions for Joe.
I cannot figure out how to indicate it, Asger, right now in the view that I have, and Joel.
So you're the boss, Marianne, so you don't have to, please.
So thank you, Joel, for this interesting presentation. I'm wondering a little bit with the graphene. I'm not so familiar with what type of compound this is. Is this something that is available, or is it something that has to be produced, or is it a natural compound, or?
Graphene, well, actually, if you've ever written with a pencil, you've probably made some graphene without realizing it. So okay. It's if you think of graphite, like we have in our pencils, it's basically an atomically thin layer of carbon, and the graphite is just stacks of that. So the trick is to somehow isolate a single atomically thin layer off of that stack. And in the original experiment, I believe it was just using Scotch tape, they could pull it right off. And
Okay.
that got the Andrei Geim and Konstantin Novoselov the Nobel Prize in 2010.
Yeah.
So, then since that time, of course, there's been tons of developments in how you actually make the graphene, and there's always this quest for superior quality. Like I was talking about with the metals, having a purely crystalline structure without sort of having wrinkles or defects. Already that will help a lot in terms of having higher quality Plasmon resonances, for example, or whatever other application you're interested in. Yeah, so I guess in principle, Scotch tape is all you need, but then to get sort of the high, well, actually the quality is even sometimes better in the exfoliated graphene than the chemically grown one, but that's another story.
Yeah. Yeah.
Christine is raising her hand, so please, Christine.
Yeah, hi, and thank you for a really interesting presentation. And I just love this basic science, curiosity-driven research, but of course also working in global health. I would like to hear your thoughts on how, on the general applicability of this research, and maybe just asking the question which maybe unfair question. I know that that's a little internal discussion in DS also, but the question whether which sustainable development goal you would achieve along the road with this research, or attack along the road with this research.
Right. Yeah, that's a good question, actually. I mean, just from the way I sort of started the talk, I guess it's clear that I'm thinking a lot about just energy efficiency. That's sort of a big topic. Ultimately, this isn't something that will happen overnight, but if we find ways to replace more and more of the electronic components what we use in our everyday lives with optical ones, particularly in information and communication technologies, that will definitely help a lot. In terms of the biology, the biggest application, the one that we normally point to in nano-optics, is this optical sensing. So if we're able to use these optical resonances on the nanoscale to detect certain molecules that you may use to detect certain types of diseases, or actually there's now a lot of interest in even exploiting the thermal properties of these plasmonic nanostructures, because they absorb a lot of light energy. That light energy is converted ultimately to heat. And if you can find a way to put these particles into, say, a cancer cell, you irradiate with infrared radiation, and it will literally cook the cell from the inside out. And that's being used, there's been a ton of research in that area, and it's actually starting to show a lot of promise. So I think there's really a lot of possibilities. And once you're talking about things on the nanoscale, you can kind of leave it to your imagination and try to think of just having this tool that allows you to direct where the energy goes on very small length scales. Suddenly opens up a ton of possibilities in all different areas of research.
Thank you. Look forward to it.
Me too.
Gufei?
Hi, Joe. A nice talk.
Hey, thanks.
Just I have a few technical questions here. Because I never touched graphene, and you mentioned by doping they changed graphene, which is a semi-metal, they changed it to a metal. Mm-hmm. What kind of dopants do they use?
Yeah, mainly I'm talking about just electrostatic gating. So okay. Like the graphene like is bits. One. Yeah, exactly. Like it's half of a parallel plate capacitor, and it collects the charge. But there's also ways you can do it chemically. Yeah. This is maybe not as appealing in the sense that you lose that ability to actively change it, yeah. Right? So that's I'm focusing more on that. I mean, as a theorist, to me, the doping is sort of a number that goes into the simulation. But I'm always trying to use like a realistic values. There are upper limits to how far you can push that, how many electrons you can really cram into a 2D graphene sheet. So usually we stick to the Fermi energy up to 1 eV or so. That's already kind of exotic. So chemical doping can give you high energies, but then you start to sacrifice the active tunability.
Okay. And one thing I just came up in my mind is that because graphene, you're making use of graphene mainly because it has a two-dimensional electron gas with high carrier mobility, right?
Mm.
Yeah. In this sense, did anybody try to make use of the two-dimensional electron gas, like at the interface of semiconductors, like gallium arsenide and aluminum doped gallium arsenide?
Yeah, there's some, not me really, but definitely that's been studied, and you can even have really amazing mobilities in those systems as well.
Okay.
The main advantages here, like with the plasmons and graphene, like having a truly 2D system really does enhance the confinement. And then a lot of the physics I've been discussing, I guess I don't have a slide nearby, but a lot of it is coming out of the fact that you have linearized, just to example, velocity. You have energy, you dramatically change the thermal distribution of electrons. These kinds of phenomena are really appealing, but definitely doping semiconductors can also give you this kind of 2D electron gas. But it's a give and take. Depending on your application, you may want to use one or the other.
Just one comment in response to Mariana's question, because I'm an experimentalist. So actually nowadays they can grow wafer-sized graphene.
Mm-hmm.
They can use chemical vapor deposition to grow wafer-sized graphene onto copper and then transfer it. But then structural defects, like grand boundaries, essential. Yeah.
Thank you. There's a curious question from Torbjørn.
Sure. First of all, thanks for brilliant lecture. Second, you've been after energy efficiency here, but my question is basically, are there other properties? I get that. I think that what sets the scale for energy efficiency is the layers in the stack. The fewer, the higher the efficiency. Do you lose other properties that might be interesting?
So, I mean, in the context of graphene, that's actually quite true. I mean, just by adding, once you make, for example, bilayer graphene, you already have a totally different electronic structure, and then you have a lot of different electronic and optical properties. And then there was this recent demonstration that if you just twist it by about 1 degree and you cool it down to 0 Kelvin, thereabouts, you can have a superconductor. So there's definitely, the sort of different regimes and things you might be sort of winning on or losing on, depending on, say, the number of layers. For this research in plasmonics, like having these really actually 2D materials gives you already more intense light confinement, and that's kind of the figure of merit that we're focusing on here. But yeah, it really does sort of depend on your application. And then again, as I was sort of telling Gouffet, like a lot of the nice physics, in particular this nonlinear optical response in graphene, by having this shape of the band structure, you win just by having that shape. And if you start to change it, then you won't have that shape. So you might lose something there.
Maybe one can read in your overview paper about other properties related to the number of layers.
Yeah, or the references therein. I'm normally focusing on the 2D material, like the really just monolayer graphene. But well, actually, I should say though, the more recent work that I've been doing also with collaborators at ICFO is to look at these thin metal films that contain a few layers of metal monolayers, down to maybe 5 or 10 or something. And here we're finding already that you can sort of engineer the nonlinear optical properties just by changing the thickness. So that's one way to do this.
Thanks.
For nice talk. So I have, again, maybe a little bit of technical question, and want to hear how you think. So you discuss a lot about the graphene and its nonlinear properties, which is known, and it's great. But also you have mentioned slightly about the other 2D materials, and in particular we have TMDs, different types. We have these group 4 monochalcogenides, and they also, at least some of them, they can be they can show some strong nonlinearity, and of course they can also have let's say second order nonlinearity, which is not there in case of graphene, at least in the dipole approximation. So how do you think, what do you see the prospect of these two if you want to compare, because each one has its own, let's say, advantages or disadvantages?
I mean, you've kind of answered my question for me in a way, because that's exactly what I would say if you had just stopped halfway through. That exactly, like you have the breaking of centrosymmetry and the different crystal lattices. Also, I mean, what I'm really interested to know about more, and this isn't where I haven't been working so much yet, but would be like if you have the exciton polaritons that are incredibly long-lived, they have huge transition dipole moments, they can also give rise to intense optical nonlinearities. So even, I mean, I'm not so interested to just compare numbers and see which material gives such, you know, if it's 5 or 10 times greater, but just the fundamental interaction, whether it's way more nonlinear or not. And even interfacing them in different ways could be appealing. For example, I was taking some, let's say, baby steps in that direction. If you think about interfacing like a quantum emitter with a graphene nano island, but then imagine if it's just a 2D sheet of graphene with a 2D atomically thin semiconductor. You can have the same kind of physics, but then you'll have polaritons that can actually propagate, right? So then the game changes a lot, and this is kind of a direction I really want to pursue. I think it has a lot of potential.
Thank you so much.
Hopefully that answers your question.
Yeah. Yes.
Okay.
Sure. Thanks.
So in the interest of time, I think we have to round off now. I would like to thank Joel for giving a wonderful talk, and everybody for participating. Let me also finally remind you that next week, same time, we have Caroline Löscher giving a similar lecture with possible implications also for our issues in terms of climate changes. So please also join next week. And with this, thank you, everybody. Thank you, Joe.
Thank you. Bye, everyone.